looks like, yeah, everyone's back at their desks and it's 4:30, so let's go on with the last talk of the day. So very sensibly, Dale suggested that we do 4 talks a day to keep everybody from, Zoom fatigue. So here we are already, the last talk of the day. It's going to be Bar-Natan talking to us about Kashaev's signature conjecture. So please take it away.
Okay, so let's start. So first of all, my agenda is show and tell with signatures. And if you know the phrase show and tell, it usually comes from childish contexts where, children bring their teddy bear to kindergarten. And that's roughly it. Namely, I barely know what our signature. I just learned. I've learned of a conjecture. I want to show it to you. What I'm adding is absolutely minimal. It's an intentional childish agenda, or I'm conscious that it's a childish agenda. Anyway, I will display 2 computer programs on the screen. And both of them, they look nearly identical with small, tiny modifications between them. And they compute the same thing, but me and the student I'm working with, Sina Abbasi, who actually you can see, don't know why they compute the same thing, and neither does Kashaev, who came up with the second one. So seems to be still an open problem. If you can, please turn your video on. I'd love to see you. And all the slides and all the codes that I will show in my talk are available at this URL. It's also on the upper corner of my screen. And I'll also post the video there eventually. I am taking a video right now. So here are the 2 programs. I don't have much to say. This is the program written in Bedlewo. No, I do have much to say, but I'll say it in a moment. This is the program I wrote in Bedlewo in Poland in 2003, slightly modified and modernized and highlighted. This is the program that computes the Kashaev invariant. I don't know why they produce the same output. But first of all, why am I showing you code? This is math. We kind of think of code as like sort of a version of hell. But I love code. Sorry, if I'm unusual, if I'm strange, so be it. I love code. Believe it or not, it's more expressive than math talk. I mean, just notice how concise are these programs. And I see it again and again. And finally, it's directly verifiable. Once you look at the code and it runs and you compute the invariant and it works for all nodes with up to 10 crossings, you know the conjecture is true, and furthermore you know that there are no typos in the handout on which the conjecture is printed. So I love code. Anyway, back to the programs. So again, the 2 programs are the Bedlewo program on the left, the Kashaev program in the right. All I want at the moment is to show you the differences. So one is called Bed for Bedlewo, the other is called Kas for Kashaev. Both of them take as inputs a naught and omega, which is a complex number of absolute value 1. Both of them define 2 variables, t and r, well, t and r here, and u and w and v here, but they're really just minor formulas made out of omega. I mean, I just wanted to simplify the matrices below. Both of them end up having some 4x4 matrices in them. And this is where the big difference is. And finally, one produces a matrix A and outputs its signature, namely the number of positive eigenvalues minus the number of negative values. The other one outputs the signature minus the right of the knot divided by 2. And the output overall is the same. Well, let's first verify that the output is the same. as a way of telling you that there are no typos here with absolute confidence. Okay, this is it. So I load a standard knot theory package just so that I'll have a database of all the knots. I define a little program to compute matrix signature. Basically, it's the sum of the signs of the eigenvalues of the matrix, except I exclude the eigenvalues. I restrict my attention to the eigenvalues bigger than 10 to the minus 12 for numerical stability. It's a minor issue. And I write a little program to compute the rise. Basically, if the knot is positive, you add 1. If the knot is negative, you add negative 1. And then I let the computer set omega to be the exponential of a random real between 0 and 2 pi, and test if Bedlewo of k and omega is equal to Kashaev and k and omega. I do this 10 times for each knot, and let the knots run from all knots between with 3 to 10 crossings. There are 249 knots. I test each one on 4 random units. So I get 2490 times the answer true, and there is no doubt the conjecture is true. There's just no doubt. Anyway, but now I want you to actually understand what is going on. So first of all, how the programs run, and then how would mathematicians say it. So first of all, you label everything. So if you're given a knot, I believe this is the knot 8-2, the first thing I do is I label all the edges in order. So 1, 2, 3, 4, 5, 6, 7, well, I mean, you can look at the ordering. And then one standard presentation of the knot is to list the edges around each crossing going counterclockwise, and by convention I start from the incoming lower edge. So this crossing here is the incoming lower edge is number 10, then 1, then 11, then 2, so it's 10, 1, 11, 2. The next crossing is 2, 11, 3, 12, so 2, 11, 3, 12, and then there are 6 more crossings which I'm not displaying. And then here is the label everything bit. So first of all, not only I want the edges label, I label the sides of the edges. So every edge has 2 sides, and my convention is to label edge 13, the right-hand side of it, by 13, and the left-hand side by negative 13. So here you see all 32 edge sides and their labels. So if this is edge 6, it's labeled 6 on the right and negative 6 on the left. Then that divides the plane into regions. All the regions here are shown in green, and they're all oriented counterclockwise, including the one at infinity, which is counterclockwise relative to infinity. So to you it appears like it's oriented clockwise. And I also want labels for the armpits. The armpits are, well, you see, if you have a crossing, every crossing has 4 armpits. Okay? And my convention is to label an armpit by the label of the edge that is right before it, using the counterclockwise orientation. So the armpit over here is labeled minus 14 because the edge before it is minus 14. Okay? And then that gives me an alternative presentation for the knot. Namely, I can go over the crossing. Each one is either positive like these two or negative like all the rest in this picture. And then so for the first crossing, this one, I label it x minus because it's a negative crossing, and the armpits around it are negative 1, 11, 2, 10, 2, negative 10, so negative 1, 11, 2, negative 10, and my convention for armpits is to start labeling them from the region between the two incoming strands, right? So if you have, well, I think I said it well enough. And then the last thing I want to mention is that there are also bends. A bend is basically where one edge side meets another, and it's just a path. All that it is a path, and but I labeled it as a path from edge side -6 to edge side -10. And then there are lots of other bends in the picture, 32 in fact, but I've only labeled one. Okay, so now how does the program work? Let me just run the code for the program line by line, and you will see how it works. So first of all, here is the note 8-2 once again, and here is the full PD notation for it. So I decree that the PD notation for 8-2 is this, and you can check. So 10, 1, 11, 2, 10, 1, 11, 2, and so on. And furthermore, since the program refers to a note K, I set K to be 8-2. And now the actual program begins to run. So in fact, if you look back at the program, maybe I will look back at the program. The programs look like, there are several lines of code, then there is a single do loop, and then there is the output. So I'm just going to execute these lines one by one in front of you. So first line is you set a variable called crossings by armpits, and you declare it to be, well, it's just the PD notation of the note, what we had before, to which you apply the rule that a crossing of I, J, K, and L, if the crossing is positive, a crossing X, if it is positive, you map it to X plus minus I, J, K, minus L, and if it's negative, you map it to X minus of minus J, K, L, minus I, and you can easily tell by my conventions that simply converts the PD notation to the armpit notation. So indeed, the output is the 8 crossings listed by armpits for the note. So for example, X plus minus 16, 8, 1, minus 7 is, I believe, this crossing. Okay? A positive crossing where we start at minus 16 and then we have 8, 1, and minus 7. The next thing I do is I create a list of all the bends. And you can check that if you have a crossing and its armpit notation contains a 10 followed by a minus 6, the corresponding bend is minus 6 followed by minus 10. So basically, to get the list of all the bends, all I have to do is to take every crossing, and if the crossing has armpits A, B, C, and D, the bends will be a path from A to minus D, a path from B to minus A, a path from C to minus B, and a path from D to minus C. When I do it to all the crossings, I get a list of, I believe, 32 bends. And now comes the first clever, so far it was just notation. Now comes something a little bit clever. Wherever I see a path going from X to Y, followed by a path or along with a path going from Y to Z, I convert it to a path going from X to Y to Z. Done to this soup of paths, done repeatedly, basically I connect all the bends to basically I connect bends that should be connected, and that creates a list of cycles or of faces. So now I've generated a list of faces in the knot, and there is one face called -13, 4, -13, another face starts at -11, goes to 2, goes to -11. Maybe I'll go for one of the interesting one. So this face here, -10, -2, -12, -4, which one is it? I think it's this one, -10, -2, -12, -4. Basically, I generated a list of the faces. Then I make an empty matrix, so a table with zeros in it, and all it has, and whose dimensions are the faces. So basically this is a matrix which is indexed by F on the left, and so basically rows and columns are indexed by the faces. And then the next step is to do a do loop. So I run the do loop step by step. The do loop is, well, you run over X, running all the crossings by armpits. So I'll just do it 8 times. So first of all, I let X be the first crossing by armpit. So basically this is the first crossing. And let me remind you that this is the list of faces. And all I do is I ask the computer to find for each armpit which face does it belong to. Find the position within the list of faces of the corresponding armpit. And I get 8, 10, 2, and 9. So basically armpit number -1 is on face number 8. Armpit number 3, so 2, is on face number 2. So that's this 2, and so on. And then I take the matrix, and at rows indexed by the indices that I just computed, and columns indices listed indexed by the indices I just computed, namely by at rows and columns 8, 10, 2, and 9, I add the matrix VU, 1U, well, these 4x4 matrices, depending on the sign of the crossing. So if it's a positive crossing, I add this. If it's a negative crossing, I add that. And now my matrix becomes that. Now I will not bore you by doing it 7 more times. I'll just let the computer run over the rest of crossings by armpits. And the result is a matrix A. This is the matrix I will be working with. Okay? Now, here's what I do with it. So I set omega to be e to the it. I set u to be the real part of omega, of the square root of omega, v to be the real part of omega, and I plot the matrix signature of this matrix minus the right of the knot divided by 2 as the root of unit, as the unit runs along the unit circle. So as t runs from 0 to 2 pi, and here is the result. And if you've seen Levin-Tristram signatures before, this is roughly what they always look like. And in fact, the Bedlewo program, which is essentially the same, the only difference is that the matrices are different, produces the same output, as you would expect, as I'm asserting. Here is a different way to say it. Here's how a mathematician would say all the same, or the same things. So the Kashaev invariant of a knot at a complex unit omega, namely at a number omega whose absolute value is 1, is computed as follows. First of all, you set lowercase u to be the real part of the square root of omega, and v to be the real part of omega. Then you make an f by f matrix where f stands for the set of faces, and the matrix has contributions 1 per crossing, or each crossing contributes to the 4x4 submatrix defined by the faces adjacent to that crossing. So if the crossing is positive like here, the contribution is, the contribution to the entry between the face here and itself is V. The contribution to the entry from this face to that face is 1, and so on. And for negative crossings it's the same but with minus signs, and then you output 1/2 of the signature of the matrix minus the right of the knot. Similarly, the Bedlow program does the same, except different local variables. So t is 1 minus omega and r is twice the real part of t. You again make a face-by-face matrix, and the entries of the 4x4 contributions per crossing are summarized here. This is a complex matrix now, so and it's not symmetric. So the way I wrote it is, if you want the entry at the corresponding to row this face and column that face, you follow the arrow between the two and you get 2t. If you want to go backwards, you conjugate. Okay, if you want to yeah. So why are these two things equal? Well, I don't know. I genuinely don't know, and neither does Kashaev. It shouldn't. Well, I mean, the basic temptation should be draw is really silly. I mean, it's just a simple-minded matrix manipulation, but it's not a stupid simple-minded matrix manipulation. It might be a more complicated simple matrix manipulation. It cannot be a simple matrix manipulation because, well, one is over the reals, the other is over the complex numbers, but the bigger thing is that there is a factor of 2 in the signatures between in the signatures that you're actually measuring. So somehow the Kashaev computes twice the signature, not quite the signature, and the shift. So it's not a simple-minded matrix manipulation. And the last thing I want to say is that the Bedlow program computes the Levin-Tristram signature of a knot K at a unit omega. And the sketch of the proof is really easy. So, but well, basically you almost follow the definition. So it really is a childish show and tell at the end of the day. Levin and Tristram tell us to look at the signature of 1 minus omega times L plus 1 minus omega conjugate times L transpose, where L is the linking matrix of a ciphered surface for the knot, meaning Lij is the linking number of a curve gamma, of a curve gamma I with its push out from the surface, and where the gamma i's run over a basis of H1 of the ciphered surface. But signatures don't change if you run over an overdetermined basis, namely if you run over a generating set which isn't necessarily linearly independent. And the reason is that this just adds linear dependencies between the rows and the columns, which means 0 eigenvalues. So I don't need to go over a basis of H1, I just need to go over a spanning set of H1. And basically, let me remind you how you construct a ciphered surface. So one way to construct a ciphered surface of a knot is to first look at its oriented smoothing, then turn every line in the oriented smoothing into a vertical curtain, and then connect places that used to be adjacent in the smoothing, connect them with twisted bands like here. And then the last step is to seal off the bottom with discs, but I don't care about this. I mean, this makes H1 smaller, and all I care is that H1 will be big enough. So I don't seal the bottom with discs, and I just compute the linking matrix for this surface. Now, H1 of this surface is generated by the faces of the of the diagram. Each face contributes to H1 of this surface, and it's very easy to check that the linking matrix of those face contributions is determined by a contribution from each crossing, and that contribution is exactly the contribution that the program computes. So here you go, a nearly childish problem about signatures that I don't know how to solve, and that is advertised as an open problem in a paper by Rinat Kashaev from 3 or 4 years ago. That's all.
Hey, thanks very much.
I hope you didn't suffer too much when I went through code. Yes.
Oh, that's great. Are there any questions?
So you basically, it's like sort of computing the Tristram-Levin signature from a spanning, like from a black and white, from the checkerboard surface, right?
I didn't say checkerboard anywhere here.
Yeah, I know that
But-
you didn't. But your last slide, that's what's happening, right? Can you go back one?
Yes, in my last slide. No, it's not the checkerboard. I use all the faces, not just the white faces or the black faces.
Oh, I see.
I use all of them. Now, I don't know. So there are forms. So you see, you might think, since I use all the faces and not just the blacks or the whites, that's why I'm getting twice the signature. Okay, that's why the Kashaev formula computes twice the signature. That makes sense, but I couldn't make it work. I mean, the matrices are not the Goritz matrices. I'm actually not even sure if there is a checkerboard formula for Levin-Tristram formulas.
I don't think there is, because when I was a student, I had a written examination in not theory. And
Yeah.
I wish I had this something like this to compute the signature.
Yeah, actually, Cameron, do you know if there is a Tristram-Levin formula for using checkerboard colorings?
Yeah, it's a good question. I imagine you would think there would be. I mean, I imagine for the roots of unity there probably are, right? Probably is.
So this is so this is like a Goritz formula for
Right.
Tristram-Levin.
Absolutely.
Except it's a Kashaev formula, not a Goritz.
Right.
But Cameron's paper was just about the regular signature, right?
That's correct, yeah.
So this would be for higher covering sort of thing.
Yeah, I mean, I think for roots of unity, you as you suggest, you go to the second branch covers, right? And then there's probably going to be an analogous formula, yeah. For an arbitrary complex number on the circle, yeah, maybe you have to do some, yeah, I don't know.
But let me say, I mean, this is so stupid. Sorry, oops, my remote stopped working. Just a minute. Where are the two programs? Here. This is so stupid. So stupid. The proof has to be equally stupid.
Yeah, I mean, you're absolutely right. It's exactly the analog of the, I mean, it's the Goritz matrix, and then the ride is that's the Euler class of the, of the normal bundle on the boundary and so on. So yeah, I mean, yeah. you would think it would have to be approved. Yeah. We're done.
Okay.
Are there any other questions? Any other discussion?
Dror, what language are you using here?
Oh, it's Mathematica.
Uh-huh.
If there's no other questions, let's thank Dror again. So thanks
Thank
very
you.
much. And that wraps